Welcome to today's explainer. Look, if you've been paying any attention to this massive boom in artificial intelligence, you know that modern AI GPUs generate an absolute unfathomable amount of heat. I mean, keeping these facilities cool is literally a 24/7 battle against the laws of thermodynamics. But, while everyone's out there hyping up the massive chillers and those high-tech liquid cooling systems, there's actually an unsung hero quietly sitting right outside the facility. It's the thing making sure the entire AI revolution doesn't, well, literally melt down. So today, we're diving straight into the incredible engineering behind the buffer tank. Okay, let's dive right into this. 2 to 10 minutes. That right there is the crucial window. Now, you might be thinking, hey, in a world-class data center, if the power flickers, the backup generators just instantly kick in and everything's totally fine, right? Well, kind of. The electrical power might be fine, but the cooling? Totally different story. You see, even when those massive emergency generators turn on, the heavy-duty chillers that actually produce the cold water for the whole facility need to go through an intricate safety sequence just to restart. They have to protect their internal motors, they got to stabilize their oil pressure, the whole shebang. Because of this, it takes a bare minimum of 2 minutes and sometimes up to 10 whole minutes for a chiller to fully reboot and actually start supplying cold water again. So I really want you to think about the stakes here for a second. What actually happens if the cooling simply stops for 5 minutes? We're talking about incredibly high-density server rooms, packed wall-to-wall with AI equipment that run insanely hot. If that flow of chilled water just ceases, the temperature inside the white space of the data center is going to skyrocket in mere moments. It's basically a terrifying ticking clock. Within just a few minutes, those multi-million-dollar servers will literally be forced to execute a devastating thermal shutdown just to protect themselves from melting into a puddle. Section 1. The Golden Time of Blackout. And this brilliantly illustrates the massive, honestly quite dangerous gap engineers have to bridge. Let's look at the exact timeline of a blackout. Right at 0 seconds, boom, the power fails. Within about 10 to 15 seconds, those massive diesel backup generators roar to life. But even though we have power again, that chiller restart delay we talked about, that just started. We are now officially in a cooling blackout. By the time we hit the 5-minute mark, we're in a full-blown thermal shutdown crisis. This timeline shows us a terrifying void where the servers are just blasting out massive heat, but absolutely no new cooling is being produced by the chillers. And that terrifying gap is exactly why a concept called ride-through is absolutely vital. Ride-through is this critical operational window where emergency chilled water literally must be supplied while the main chillers are offline and booting back up. Think of it like CPR for the data center, right? When the heart of the cooling system, the chiller, temporarily stops beating, you still desperately need oxygen, or in this case cold water, to keep the brain alive. The buffer tank acts as that mechanical life support system. It provides this ride-through, keeping the servers breathing until those chillers finally come back online. Section 2. The giant thermal battery. But here's the thing. Providing emergency water is actually only half the story. We really have to look at this tank as a highly dynamic energy storage device. Modern AI data centers, they are incredibly unpredictable. Unlike older, traditional data centers with steady, boring workloads, AI servers running high-performance GPUs, like the H100 or the B200, they have these wild minute-by-minute fluctuations in their computational load. And naturally, that means wild fluctuations in their heat output, too. Now, if the total volume of water in the cooling pipes is too small, these sudden heat spikes will cause the water temperature to just swing wildly out of control. The chillers then try to furiously chase these rapid temperature changes. It's a huge headache that engineers call hunting, and it leads to extremely unstable capacity control. But by adding the massive water volume of a buffer tank, we create thermal mass. It acts as a massive thermal buffer zone that absorbs those sudden spikes and keeps the entire system nice and stable. Let's move to Section 3, the magic of unmixing. Now, you might be wondering, wait a second, if we have perfectly cold water stored up for an emergency and boiling hot water constantly coming back from the servers, how on earth do we keep them from mixing in the tank and ruining our cold supply? Well, the secret here is a little thing called thermal stratification. This is a super elegant physical principle where cold and hot water naturally form separate, completely unmixed layers. It's just density. Cold water is denser and heavier, so it sinks right to the bottom. Hot water is lighter, so it floats on top. It is such a brilliant contrast. I mean, while the server rooms inside are chaotic, super loud, and blasting out heat, the water inside the buffer tank out back is perfectly still, entirely silent, and flawlessly layered by nature. let's actually walk through the exact steps of how this plays out during a crisis. So the power fails, the chillers stop, but the server rooms are still pumping out hot water, typically around 15 degrees Celsius. Step 1. This hot water is gently, and I mean very gently, pushed into the very top of the tank. Engineers use these specially designed pipes called diffusers to make absolutely sure the water enters smoothly without creating any vortexes or turbulence whatsoever. Step 2. As that hot water fills the top, its downward pressure perfectly pushes the stored, still 7 degrees Celsius cold water out from the very bottom, sending it straight back to the server rooms. And step 3, because there's zero turbulence, this pristine thermocline layer forms. It's basically an invisible boundary where the hot and cold water meet, but they simply do not mix. It literally allows the tank to act as a perfect depletable thermal battery. How cool is that? Section 4, Secret of the Thermal Buffer Zone. Now, what's really interesting about this is relying on physics is great and all, but to make this actually work during a catastrophic blackout, you need flawless automation and highly specific power sources. Think about it. The chillers require massive amounts of power, so they're stuck waiting for the delayed diesel generators. But the buffer tank's cold water can't just sit there doing nothing. It needs to be moved right now. That is exactly why the secondary and tertiary chilled water pumps, the motorized valves on the tank, and the CRAH fans blowing the cold air over the servers, they are all hardwired directly to the UPS, the uninterruptible power supply. That battery-backed UPS ensures that the very second the power grid fails, these pumps and fans don't skip a single beat. They instantly draw that life-saving cold water from the buffer tank, ensuring absolute continuity of cooling. Section 5. Designing the Last Bastion. Okay, so we know how it works and we know how it's powered, but how do you actually plumb a massive multi-ton tank of water into a giant hyperscale facility? Facility designers generally have to choose between two major piping methods, 4-port and 2-port. A 4-port or inline system means literally all of the facility's water flows through the tank at all times. The pro here? Excellent load absorption. It is incredibly stable. The con, though? Having to push all that water through a giant tank 24/7 causes constant pressure loss, meaning your pumps have to work way harder and burn way more electricity. On the flip side, the 2-port or bypass method sits alongside the main pipe. Normally, water just bypasses the tank entirely, which means zero pressure loss and super high operational efficiency. But when a blackout hits, you suddenly have to rely on a highly complex automated sequence of motorized valves to instantly redirect the water through the tank to maintain that thermal stratification we talked about. So it's a classic engineering trade-off, right? Simplicity versus efficiency. So the crucial point really comes down to this. Just how big does this tank actually need to be? You definitely don't just guess. You have to calculate it precisely to save millions in hardware. Engineers take Q, which is the total IT load of the data center in kilowatts, and they multiply it by T, the target ride-through time, say 5 to 15 minutes. Then they factor in delta T, the temperature difference between the supply and return water, and finally divide it all by N, the tank's stratification efficiency, which is typically incredibly high, sitting at around 85 to 90%. When you actually run this math for a standard 10 megawatt data center, you quickly realize you need hundreds, if not thousands of tons of water. And honestly, this is exactly why when you drive past a modern data center today, you'll almost always see these giant vertical silo-like tanks towering outside. Which brings us to our final parting thought for today's explainer. The buffer tank is the ultimate mechanical UPS of the data center. Think about it. While the electrical UPS is busy keeping the ones and zeros flowing during a power glitch, it is the silent, colossal volume of perfectly stratified water inside the buffer tank that steps into the void to prevent a catastrophic meltdown. It literally buys those precious golden minutes for the chillers to wake back up. So the next time you're reading about the massive, mind-bending computing power of AI, take just a quick moment to respect the simple, beautiful physics of the giant water tank keeping it all alive. Thanks so much for joining me on this explainer, and I really hope you walk away with a whole new perspective on what it actually takes to keep the cloud cool.